Welcome everyone to Phoenix LiDAR Systems December 2021 webinar. The topic this month is LiDAR snow surface mapping for the NASA SnowEx program. Our host today will be Jeff Rizza with DJ&A and Conrad Quintera. And with that, let's go ahead and get started. Conrad, take it away.
Thanks, Abby. Hello, everyone. Yeah, thank you so much for joining us today for the final installment of our 2021 webinar series. I hope it's been a great year for you all and that you've enjoyed some of our presentations so far. Please stay tuned for many more upcoming through next year. As many of you know, Phoenix LiDAR specializes in designing and building compact and flexible mapping systems. We offer a range of products that fit many different applications and different scales of operation. Our solutions include everything that you'll need to successfully plan, acquire, and process data to the highest standards. Here at PLS, we're always focused on what users need in order to achieve their objectives. Our accomplishments have pushed some boundaries, but more importantly, they've helped many clients to successfully utilize LiDAR-based remote sensing payloads within their own domain. We really strive to ensure that you're going to have the right tools for the job, and we very highly value the partnerships that we're a part of. In today's webinar, like Abby said, we're going to give the spotlight to Jeff Rizza from DJ&A, who's been using a Phoenix system for around 4 years now. Jeff will be discussing a very interesting snow surface mapping project that they've worked on this year. So welcome, Jeff. Thank you so much for taking the time to join us and to share your work.
Yeah, thanks, Conrad. Thanks for having me on. Appreciate the opportunity to share this project. I think it's a pretty cool project that we completed earlier in 2021. And I'm just going to grab the screen from you here so we can jump into it. Okay, how's that look to you guys?
Looks good, Jeff.
Okay, did you have some questions you wanted to jump off with on this slide, or did you want me to just go ahead?
I think you can go ahead. These are the topics we're going to cover in the webinar. So yeah, take it away.
Yeah, so like I said, we're going to cover the SnowEx project, but I do want to just give everyone a little bit of background on myself and our company quick beforehand, at least some of the relevant background on myself. So I got into using UAVs for mapping and other research applications in undergrad. I went to Hobart and William Smith colleges in upstate New York. It's a small liberal arts school, and pretty quickly got into using drones for, we were mostly doing mapping of aquatic invasive species, and there was some interest in using things like multispectral sensors to detect blue-green algal blooms in a lot of the lakes in that region. And so we were using commercial drones at the time. This was like 2013, 14, so a lot of DJI products, of course, and then also building some custom UAVs and custom sensors to do that work. Sort of the next blip on this timeline that occurred really simultaneously while I was in undergrad and grad school was, as a physics major, I was involved in NASA's student engineering and science program called RockSat-C and RockSat-X, which is a program that allows students to design and build their own scientific rocket payloads. So we built a couple of different sensor payloads that we launched multiple summers in a row from rockets at the Wallops Flight Facility in Virginia. So specifically, we were looking at making muon detectors. Muons are particles that are basically like really heavy electrons that come through the atmosphere. And we are also doing some spectroscopy, measuring the different wave bands that are coming through the atmosphere, reflecting from sunlight. So after graduating, I moved to Montana, and I had a brief stint with Measure, which is a drone services company some of you may be familiar with. I think they were recently acquired by Ag Eagle. I was the chief pilot for their High Plains franchise, so we did a lot of power line inspections, wind turbine inspections, and some topographic mapping while I was there. And then after Measure, I've been at DJ&A for the past almost 4 years now. Was brought on as the UAV program manager. DJ&A had acquired a Phoenix LiDAR system about a year before I had joined the company, and a Vapor 55 drone at the time to fly it on. And we've been expanding the program ever since. So that was a little bit of background on me. I'll give you a little bit on our company, DJ&A. We're a civil engineering and land survey company with our headquarters in Missoula, Montana. We especially specialize in roadway engineering, and our land surveying department has a lot of experience with cadastral surveys and various types of surveys like that in the Western United States. And we also recently acquired an environmental consulting firm. So our company is growing quickly. As I mentioned, our headquarters is in Missoula, Montana. That's in Western Montana. But we've opened an office about 5 years ago or so in Vancouver, Washington, and we've recently opened offices in Denver and Sioux Falls, South Dakota. So we're mostly located in the Northwestern United States, but we do work all over the United States. Most of our clients are federal agencies, like the Forest Service is our longest standing client. The company was actually founded in the 70s by some retired Forest Service engineers. We do a lot of work for the National Park Service, agencies like the Federal Highway Administration, the Army Corps of Engineers, and the Bonneville Power Administration. So projects for those agencies take us all over the US.
That's really cool. I think we mentioned earlier, or you kind of spoke about your experience with the Phoenix system, but when did DJ&A first begin utilizing LiDAR?
Yeah, so they first started, I guess it kind of depends on what you want to call LiDAR. We first purchased our Phoenix LiDAR system to use on a drone in 2016. But we were also very early adopters of terrestrial laser scanning technology. And we've been doing that for probably 15 or so years, 10 plus years at least. So some experience with LiDAR from that. We've also been, from the survey side, from the geospatial side, doing projects in partnership with companies like Quantum Spatial to provide LiDAR truthing with conventional survey methods for decades. So we kind of have a longer background in LiDAR, but with a modern drone LiDAR system, we've been doing it for 5 or 6 years.
And as far as the different functions of DJ&A and what you guys do, what types of projects do you utilize LiDAR for?
Yeah, so I work within the geospatial survey group at the company. And so our bread and butter as far as our LiDAR acquisitions go is topographic mapping. So we do a lot of roadway corridor work, and we do a lot of medium to large size topographic maps for agencies like I mentioned, the Forest Service and the Park Service. And those topographic maps end up getting used either by our engineers or by our clients' engineers for engineering design purposes. It may be putting in a new Forest Service road in an area where one doesn't exist, or it may be building a new dormitory on a national park site for employees, anything like that, our maps get used for.
That's cool. You mentioned earlier that you guys also use photogrammetry. What other remote sensing technologies do you use?
Yeah, so we do photogrammetry as well with drones. So that's definitely a great tool in our toolbox. We mostly use photogrammetry for planimetric mapping. We prefer LiDAR for the topography. But we also do, like I mentioned, a lot of terrestrial scanning. We also do a little bit of sonar, ground penetrating radar, and utility locating.
Yeah, thanks for the background, Jeff. I think now let's jump into what everyone's here for, and please tell us all about the SnowEx project.
Yeah, let's jump into that. So I'll just give you a 10,000 foot view of what SnowEx is first. So this is a multi-year program started in 2017 by NASA, specifically the terrestrial hydrology program out of the Goddard Space Flight Center. And it's composed of obviously NASA agencies and scientists, but also lots of scientists across North America. I'll mention later that we specifically worked with a researcher at Montana State University who's one of the contributing researchers to the SnowEx program. So it's a very big collaborative project, which is pretty cool. And it's been taking place for about 4 years now. I guess we're in the 5th year going into this winter. And the whole idea with SnowEx is to figure out better ways to collect snow data using remote sensing tools like LiDAR. But they're also testing a lot of other tools like synthetic aperture radar, photogrammetry, and different types of wavelength LiDAR and things like that. So that kind of begs the question, why would you care about mapping snow surfaces in the first place? Well, SnowEx should maybe be called WaterX or HydroX. Of course, I'm kidding, but it really is all about water. So just some of the motivating points behind SnowEx and why it came to be. There's billions of people on the planet that depend on snowmelt for drinking water and other uses like irrigation and power generation. So snow and then the water that we get annually through snowmelt is a really important resource across the globe. One of the other motivating factors is that our changing climate is causing more floods and droughts to occur. And so it's harder to manage that water resources when things like that are happening. And so it's really, really difficult, and nobody has really cracked the nut of being able to figure out how to measure and monitor the water content that's contained in snow. And that's something that SnowEx, that's kind of the holy grail for SnowEx, is figuring out how we can measure snow and track the amount of water that's going to come from it during those melting cycles. So the goals of SnowEx are to figure out new methods for measuring snow volumes and other characteristics, like I mentioned. A big one is snow water equivalent, which is kind of just what it sounds like. It's how much water you would get if you melted the snow. They want to develop remote sensing tools and different types of data analysis techniques to better measure those different snow volumes and other characteristics and get that snow water equivalent number. And the kind of long-term goal is, if this is successful and if we're able to develop new remote sensing techniques and analysis methods to be able to figure out how much water is in snowpack around the globe, and how much of it's going to melt out during those cycles, NASA would like to eventually start either a constellation of satellites, multiple satellites, or a single satellite that can collect that data from space for the entire planet or large swaths of it. So I think we should circle back a little bit and just touch on how a civil engineering and survey company got involved with a project like this. As I mentioned in the background on me, I have a little bit of experience with NASA through some of the undergrad and graduate research projects that I did launching rocket payloads. And so like in early 2020, I had heard about Quantum Spatial, which for those of you that aren't familiar is a very, very large remote sensing company. Quantum has been involved with the NASA SnowEx project since its beginning, essentially. And most of the data acquisitions for SnowEx happen on very large areas, and Quantum collects that data using airplanes and very powerful LiDAR systems. But I thought it would be really cool to be able to have a data set that was higher resolution at lower altitude using drone LiDAR. So I kind of reached out to some of my connections through my previous experience with NASA, through those student projects, and figured out one of the project scientists at NASA, Carrie Voyevich, who's in charge of all of the field missions that happen for SnowEx in the winter. And just it was kind of a cold call situation. I just shot her an email and pitched the idea of doing a small scale field site in Montana. And she liked the idea, and we figured out how to do it in collaboration with Eric Sproles, who's the researcher we worked with through the Montana State University. So that's kind of how we got involved with it. And our piece of it is a very small part of all those other acquisitions that have been going on and are still going on this year. So just an overview of the site that we were on. If you're at all familiar with Montana's geography, I've put down some of the major cities. DJ&A's headquarters is over there in Western Montana in Missoula. And our project site is almost smack dab in the geographical center of Montana in Moccasin, which is a very small town. If you're at all familiar with Lewistown, that's a slightly larger town that's right in the middle of Montana. That's basically where we were, but some of the other cities are on here to give you an idea if you're familiar with Bozeman or Billings, for example. So let me give you some of the site characteristics. The actual site we used was the MSU's Central Agricultural Research Center. So it's a agricultural research location that tests different types of crop treatments and things like that, and soil characteristics. But it was kind of in its dormant state in the winter. It was a great test site for us to use for this. We took pretty much a 1 kilometer square block to use as our experimental site, which is about 250 acres. We're in Moccasin. And this is another aspect of SnowEx. Our site represented a prairie biome in particular. NASA's interested, and the SnowEx scientists are interested in figuring out how to get those snow water equivalent and snow measurements in various biomes, because the measurement techniques needed in those different biomes vary because of vegetation cover and soil types and things like that. So for example, this year they're focused on tundra biomes and doing a bunch of acquisitions in Alaska and northern Canada. So our site was specifically prairie biome. And I'll just give you an overview of all the data that we collected. So we went out before any snowfall happened and collected a snow off point cloud. We used the LiDAR system that we purchased from Phoenix about 5 years ago for that. And then we went repetitively back to the site throughout the season from about January to March of 2021 and collected 7 different point clouds, LiDAR point clouds, while there was snow on the ground. And we tried to time those as snow events happened. So if it snowed one day, we tried to get out there the next day or the day after to capture those changes that were happening. We also collected one, and I'll kind of get into why this is important later, but we collected an additional 8th test LiDAR sample using 1550 nanometer LiDAR, which is not the wavelength that you would typically want to use for this type of work, but we had that sensor available to us and wanted to try it as a comparison. And our collaborators at MSU and the collaborators at NASA were very interested for our particular site because we could gather such higher data density using a drone to be able to try and make this as highly accurate and precise as we could. So I kind of want to dive into some of the methods we developed for being able to do that. But this is just an overview of our site. And I'll just call out, there's a windbreak made up of shrubs in the back here. And I'll show you some point cloud data that we found that was pretty interesting around that area later on. So just keep that in the back of your mind. But kind of this whole area that we're seeing here was the test site. So these are just some close-ups of some of the conditions we were dealing with and what we were trying to map. You can imagine, if you're at all familiar with LiDAR processing or using point clouds to extract a surface, these crops sticking up through like the partial snow cover actually presented a pretty difficult challenge for us on the processing side to get a surface that included only the snow and not these various grasses and crop stubble that's sticking up through it. However, that is very representative of a prairie biome, which is one of the reasons that the SnowEx researchers wanted us to do a test on this site. So I'll just cover the equipment we used. On the left is our typical setup. This is the setup DJ&A uses to do all of our topographic mapping with. So we have a FreeFly Alta X quadcopter, and we have a Phoenix Ranger LR system, which is based on the Regal Vux 1 sensor. So that's the 1550 nanometer laser that's used in that LiDAR system, and that's what we're typically using all the time for our topographic mapping. The problem with that is 1550 nanometer light, which is a specific band of infrared light, is absorbed really well by snow. So it's a very poor sensor to use for snow mapping. Unfortunately, it's great for topography, but not the right wavelength for snow mapping. So for this project, we actually rented a Minivux 2 based system from Phoenix, which actually uses a different infrared wavelength, 905 nanometer light with that laser. And that one is not reflected by snow as well, or it's not absorbed, excuse me. So we do get the reflections we need with that system. And just some other interesting tidbits of our setup here. You'll notice if you zoom in on that, we were obviously dealing with some pretty cold conditions and wind. So flying a drone in those types of conditions is difficult. We had to insulate our batteries most of the time. I think the coldest day we were out there, it was about -10 or 12 Fahrenheit that we were flying. So to be able to not have any issues happen and maintain our flight times, we had to insulate the batteries. And we also had to insulate the air nav box that is on the LiDAR system. If any of you have a Phoenix system, you probably know that that's a great little part of the whole LiDAR system that Phoenix has designed. And the encasement there is a heat sink to be able to keep everything cool, but it works a little bit too well when you're trying to collect LiDAR in the winter. So we actually had to wrap that up and keep it warm to prevent the system from shutting down while we were trying to collect data. So before we actually collected any LiDAR, as I mentioned, I work within the survey department at DJ&A, and NASA and the researchers at Montana State University were very interested in having this be as precise as possible. So the first thing we did was set up a survey grade control network with 4 monuments all around the site that we used to reference all the point clouds to each other to a standard baseline essentially, so that we could make very accurate comparisons between the clouds later on once we had collected them all with those varying snow conditions present in each cloud. So here's an example of one of those survey monuments. And while we're on this slide, I'll just call out, this is kind of the end of that windbreak that I mentioned before. You can get a little bit better view of what it looks like here. This is just the layout of our control monuments. You can see we have 1, 2, 3, and 4 there, kind of spread around the site. And we have a GPS base station running on 2 of those every time we fly. One of them is just a backup, but we use the GPS base station locally to process our LiDAR data for better accuracy. So here's kind of the parameters we used for all of our flights. We flew at an 80-meter altitude, which was a good balance between, being able to get our coverage done in a reasonable amount of time, but staying low enough that we could get good point density. We flew at 7 meters per second for the same reasons. Pulse repetition rate is essentially the rate at which the sensor pulses out LiDAR to get points on the ground. So we maxed that out on the Minivux's capability of doing 200,000 pulses per second. Scan rate of 47 is just kind of how fast the mirror is spinning to do those scans with the LiDAR. But kind of our guiding requirement here was that we wanted really good swath overlap between all of our LiDAR flight lines, so that we weren't really sure how the reflections were going to work off snow. This is really kind of a new thing. People haven't done a lot of LiDAR snow mapping. So we wanted to make sure we had really good overlap so that if we had to, we could restrict the use of LiDAR pulses that were pretty much just straight down onto the snow. You could imagine if something's, if a light is hitting snow at an angle, it may just bounce away and not come back to the sensor. So we wanted lots of overlap to have options there on the processing side. We also had to come up with some interesting methods for truthing the LiDAR data. So typically when we truth our data, we go around with a survey rover, a GPS rover, and take shots directly on the ground. And those just get used to perform a vertical shift of the LiDAR surface when we're all done, and also check it to make sure that it's accurate. and not, you know, skewed or floating around where it shouldn't be. But you can't do that really with the snow, because obviously it's piling up above the ground surface, and it's pretty difficult to try and hold a survey rod steady right at the surface of the snow. So what we rigged up here was a standard survey rod with a GPS head on it, and we got a laser tape measure or laser distance meter that we lined up with the reference point on our GPS head. And then what we would do is stick it down in the snow and actually shoot the laser down to a card that we laid carefully on the snow surface to not disturb it. And that would give us our height measurement from the snow surface up to the GPS head, so that we could have a truthing point that's actually on the snow surface instead of the ground underneath. We collected about 30 of those every time we did a data acquisition. We also developed another kind of quality control, what we called a 3D LiDAR truthing target. This was just another quality control step to make sure that our point clouds were all lining up with each other. So what this is it's essentially just a piece of triangular plywood, and we can balance the GPS rover on the tip of it. And if you can see in the bottom right there, there's a ACL point right there on the tip. That's how the 3D LiDAR target shows up in the point cloud. And what that allows us to do is check for any kind of rotational or translational problems with the point cloud if it's been shifted in either direction or rotated in a way that it shouldn't be. It also lets us check all the point clouds overlaid on each other to make sure that they're lining up where they should be, so that we can make accurate comparisons. So let's take a look at some of the data that we ended up with. So this is a series of all 7 point clouds that we got with snow on. The red is actually the ground that we got before any snow fell. And then every other color that's sitting on top of it is some snow that had accumulated on the day that we collected the LiDAR. So you can actually see this kind of bushy area in the left of center here is that windbreak that I had mentioned before. Those are the bushes. And you can see how on different days the snow's piling up because of the wind slowing down because of those bushes. And also how it's kind of tailing off towards the right and obviously being blown around. So what this told us is that, you know, wind obviously plays a huge part in the dynamics of snow cover in the prairie biome. And that's one of the things that the researchers wanted to capture. And we were pretty pleased with how well these turned out to show that difference. Just kind of a zoomed in view there. There's those windbreak shrubs. You can see on the left, the snow drifting pretty deep. That's probably 2 or 3 feet deep there. Those shrubs are pretty tall. And you see some kind of different characterized drifting on the right side, where it's been blown over a larger area piling up. And then on the far right, you can see kind of a windblown area where the snow really isn't present very much at all, or it's very thin because it's been drifting up in the other areas. Here's another example. This is actually all of the different days overlaid on each other. So again, red is our baseline, just the actual ground surface with no snow on it. And then every other color is from an acquisition that occurred for a snow surface on a different day. And you can see how they pile up. And this again is probably 2 or 3 feet, possibly more deep. This is kind of a trench that was on the backside of a fence line. That's what those gray dots that are kind of sticking up there, that's a fence looking end on. And we were pretty pleased with the point density we were able to get with the 905 nanometer LiDAR. The 1550 nanometer LiDAR really wasn't able to do this, which is why we were testing it. We got very few returns using the 1550 nanometer LiDAR. So it was good that we planned to rent that 905 nanometer sensor. So some of the stats, I'm not going to go into all the stats we ran on all these, all this data because it's pretty extensive, but I think some interesting points. Our point density was actually higher than I expected we'd be able to get it even with the 905 nanometer LiDAR. So We got anywhere from about 130 to 225 points per square meter on the snow surfaces, which was really great because it's able to show a lot of detail and any kind of small changes that are happening or small characteristics in the surface. But that was the total point density. So when you look at the surface point density, we only were hitting 8 to 16 points per square meter. So what that tells me is that a lot of those points that we were getting in the full point cloud were things like those grass tufts and the crop stubble sticking up above the snow in a lot of areas. So we actually had to cull out a huge chunk of the LiDAR points to be able to get the surface that was only composed of about 8 to 16 points per meter squared, which was still higher than we expected it to be able to be on the snow surface. So we were pretty pleased with that. Kind of an accuracy value for you here, RMSE-Z, which is just a vertical root mean square error value. We got anywhere from about 4 to 9 centimeters, which is about 1/10 to 3/10 of a foot, which we felt pretty good. You can see at the bottom here, we certified all of these point clouds as being able to support 20 centimeter or about 2/3 of a foot contours. NASA and our collaborators at MSU were hoping that we'd be able to do a little bit better than 1 meter resolution for contours, and I think we pretty much blew that out of the water. You know, these are about 5 times better than that. So we were all pretty pleased with that result and the level of accuracy we were able to get. If anybody's familiar with the USGS and ASPRS vertical accuracy standards, our point clouds were accurate at quality level 0 or 1, depending on the day, or if you want to go by the ASPRS standards, then it was accuracy class 3 or 4. Okay, I think that's pretty much it. We ran through a lot there.
Yeah, Jeff, that's a very awesome project, and it's sparked a ton of interest at PLS. I find it particularly interesting to think about or to see the technology that I'm dealing with every day being used for something that's really, significant for really our civilization. So I think that's totally cool. And yeah, maybe I can follow up with this list of questions that we've come up with.
Sure.
Maybe you could talk about, I know you said there were some other technologies used during SnowEx, or there are other technologies. What other types of data sets were collected?
Yeah, that's a great question. So we weren't the only people operating on this experimental site that we were at. NASA actually has, I think I mentioned very briefly early on, they're using synthetic aperture radar as one remote sensing technology they're testing. So NASA has a plane equipped with synthetic aperture radar sensors that they flew over the site on 2 of the same days that we collected data. And they've been doing synthetic aperture radar collections on all of their sites. So that's one technology that's being tested. There were a number of grad students testing methods of doing photogrammetry, just using regular imagery drones to do surface reconstruction. There was also a grad student doing albedo measurements, so like light reflectivity measurements using a specialized sensor on a drone for that. So yeah, it was kind of cool. There were a lot of people involved. Some days we had like 2 or 3 different drones in the air at the same time, collecting data at different altitudes. So it was very cool.
Yeah, that's awesome. And I think you actually covered this next one. But what time frame? You did this in about a little less than a year ago, right? And it spanned a couple months.
Yeah, it was earlier in 2021. So it was basically, we started in January of this year and went through just, I think the first week or 2 of March is when we ended. We did the last data collection.
Yeah, that seems to me like a pretty small time frame for the amount of data you collected. So sounds like a lot of work.
We were out there almost every week. Yeah.
Yeah. You mentioned, you talked about the control points that you guys were using for accuracy. Did you guys perform any other unique quality control during acquisition?
Beyond the couple things that I mentioned, no. I mean, we had that specialized rig for getting truthing points on the snow surface as opposed to the ground underneath. So that was something we had to figure out. And then those 3D control targets as well were kind of a unique way of doing quality control.
Yeah, I really appreciated seeing what you guys did with the snow surface checkpoints. I've never used that personally, so that was interesting to see.
Right.
You talked a little bit about how SnowEx is interested in different biomes, and I'm curious about the prairie biome and how that's kind of unique with respect to water resources. Do you have any insight on that?
Yeah, the prairie biome, at least as it was explained to me when we were kind of prepping for this whole project, is really actually the most common snow-covered biome on Earth. And so it's a pretty important one for them to be able to nail down the remote sensing techniques that are going to be used to get, snow measurements and ultimately water measurements there. But some of the challenges are kind of, as I touched on, the snow blows around a lot in a prairie biome. It changes, it's really dynamic. And also, like our test site was not a natural landscape. It was an agricultural test plot. So you have that challenge as well. There's a huge variety of different types of prairie biome. So there's natural, but then there's also a lot of agricultural land that counts within that category, at least as far as the SnowEx project is kind of categorizing things. But it's also very ephemeral, for lack of a better word. That the snow's very dynamic. It's blowing around, it's evaporating, it's piling up in areas and blowing off other areas. So it's difficult to develop the techniques, especially for the prairie biome, as opposed to, like a forested biome. I think your main challenge there would be getting rid of the trees that are in your way, of course, but the snow doesn't move around nearly as much.
That makes sense. Yeah, I think it's not a super common application to be measuring snow. Were there any other data-related challenges that you guys faced?
Yeah, actually, on the processing side, it was pretty difficult. It was challenging for us to figure out how to get those surfaces. And part of that was what I mentioned. One aspect, anyway, was what I mentioned earlier about the crop stubble being there and the grasses sticking up through. But that's kind of a similar challenge to regular data processing, right? You have grasses and things that are on top of your surface that you need to get rid of anyway. So those were similar, but kind of a unique challenge with this was, and this is a pretty nuanced point with LiDAR processing, but typically when you process LiDAR data on a regular ground surface, the actual ground is somewhere within like a small thickness of the point cloud that represents your surface. And so all of the software and algorithms that are made to extract a surface from your raw point cloud are built around being able to kind of pull the bottom side of that point cloud. And what we found was with snow, first of all, it's much noisier. So you kind of get LiDAR returns that look like they're penetrating deeper into the snow surface. And so you have this kind of fuzzy surface that you start with. And the actual surface we found was more towards the top as opposed to the middle or the bottom, which would be more normal. So the challenge was figuring out how we were going to extract the top of that snow surface, but leave out the grasses and things like that. So we developed some kind of custom routines and processing methods to make that work.
That definitely sounds unique. Yeah, I think we're used to seeing the effects of imprecision on ground surfaces, and typically, assigning the center of that fuzz as the ground. So yeah, that definitely seems nuanced and unique. If you guys were going to do this again, would you make any changes?
Yeah, I think so. One thing we would do, I think, is we kind of had to get started too quickly for us to set up those 3D LiDAR targets the way we wanted to. As you kind of saw from the pictures, if you remember, they were just on a set of tripod legs. And so they were semi-permanent. We put them out and they were out for like 2 to 3 days at a time when we would be there for an acquisition. But we broke them down when we would leave and then set them up again for the next acquisition. They weren't always in the same spot. What we wanted to do that we just didn't have time for before the snow fell was to set up more permanent 3D LiDAR targets that were more like on a post that was sunk into the ground that we knew was always in the same place every time. And I think that would have given us another like good check to make sure that all of our clouds, we had 8 on different days, were aligned with each other appropriately.
I can totally see that. I mean, a lot of repeat survey locations, you've got some constant, surfaces that you can compare, and your situation, your environment you were measuring was really dynamic, and that would make sense if you guys establish something permanent.
Yep.
Jeff, that was really enlightening. Really appreciate it. I'm gonna open up to audience questions now, and
Sure.
See if we've got anything incoming that we can answer.
Yeah, let's go for it.
It looks like we've got a question here saying, what type of material did you use to insulate the air nav box?
Oh,
and did you experience a drastic change in flight time with the insulated batteries? It's kind of a two-parter.
Yeah, no, that's a good question. So I'll start with the batteries. First of all, yes, insulating the batteries made a big difference. I think in those cold temperatures, we did try and do one flight or a couple flights without insulating them, and we typically get with that minivux sensor, we were getting like about 25 minutes of flight time on the Alta X when we were doing our testing in more normal temperatures. But in the colder temperatures, without insulating the batteries, we lost like at least 5 to 10 minutes of flight time. But then when we wrapped them in, the bubble wrap, which is basically what it was just like packing bubble wrap, we were back up close to our normal amount of flight time. So like maybe we lost 2 or 3 minutes to the cold once they were insulated. And then insulating the air nav box, that was actually kind of just a piece of foam that we wrapped around it and then zip tied each time. It was just kind of a temporary setup. But actually on the really cold days, the couple days that were like below 0, we stuck some hand warmers in there that you couldn't see in the photos, but there were a couple hand warmers up against the nav box to keep it warm as well.
Seems like cost-effective solutions.
Yeah.
Another question here. Can you share any details on the software tools, or what software you used during this study?
Sure. Yeah, that's a good question too. We use a lot of pieces of software to do LiDAR processing. Phoenix has their software, Spatial Explorer, that gets used for a lot of the initial steps of processing the data when it comes right off the sensor. So we use Spatial Explorer, which is a Phoenix piece of software. We also use Inertial Explorer, which is a Novatel program for some of the LiDAR trajectory processing, which, if you're not familiar, is basically you have to get a very accurate path that your LiDAR sensor traveled through space to be able to get accurate point cloud data. But for the point cloud processing, we use TerraScan, which is a program that runs on top of MicroStation, which is a piece of CAD software, basically. But TerraScan is our main point cloud processing software. And then we also use a free piece of software called Cloud Compare to do some of the QA and point cloud comparisons and things like that.
Here comes another question. How much time did one survey take from acquisition to deliverables?
From acquisition to deliverables, yeah. So it's kind of a multi-part answer, I guess, because there were so many acquisitions that happened and we didn't necessarily process them all in sequence. But the acquisition end of it it was usually a 2-day ordeal to go do one acquisition. So we would travel out from our office in Missoula to the site in about a half a day and set up those 3D targets and do some truthing. If we knew that the snow conditions weren't going to change by the next morning, we would get the truthing done that first day. Then we'd come back in the morning, do our flight, It took about 4 flights to fly the 1 kilometer squared area each time. And that would take about 2 to 3 hours from start to finish of flying. And then we may do the truthing afterwards if the snow conditions changed overnight and head back. So it was kind of like a 2-day ordeal to do the acquisition. Processing could take anywhere, once we had nailed down those specialized ground extraction techniques that I mentioned earlier, it probably only takes us a few days to get a point cloud done and totally QC'd and ready to submit to SnowEx. But we spent a lot of time in between trying to figure out how we were going to get accurate surfaces of the snow surface extracted. So there was a lot of time that went into kind of doing experimental processing in the office.
Yeah, it sounds really in depth. Here's another one. Do you know, or how do you measure snow water equivalent?
Yeah, that's a good question. So basically for snow water equivalent, you need to know the volume of snow you have, but you also need to know some other characteristics, right? Because snow is water crystals, but there's a lot of air in there. So you can't just take the volume of snow you have and convert it directly into a volume of water. The challenge is the snow conditions are very different all the time. So they could be denser, it could be less dense. The snow crystals could have different structures. And so to be able to get snow water equivalent measurements, the 2 basic things you need is a snow volume, which is what we were collecting with LiDAR. But then you also need a density measurement, and those get collected using like different types of ground-based sensors. And they're like one of the things that SnowEx is looking at is as a big challenge is there a remote sensing technique that you could use from something like an airplane or a satellite to measure the density of the snow? And that's, I think, things like the synthetic aperture radar is one thing that's experimentally being used for that. And there's some other measurement techniques that I'm not as familiar with that I think are being used to try and collect aerial measurements of snow density, if that answers your question.
I think that's interesting to see where things go in the future and what's achievable.
Mm-hmm. Yeah.
Another question is, do you think you lost point density due to the temperature?
I wouldn't say due to the temperature, it's exactly, but I think we had a really large variability in point density, which you guys didn't quite see in the slides because I kind of just gave you the high level overview of the stats, but the snow covered clouds from day to day varied a lot in their point density. And it wasn't obvious why that was happening. I did see if there was a correlation to like temperature and humidity, because those were things we collected, which there wasn't a correlation there. But I think what it probably is due to is the snow surface, like crystal characteristics, right? Like what the snow crystals look like. They may be more reflective, or they may absorb light better on certain days. If the snow's really fluffy, for example, maybe a lot of the LiDAR light gets lost in that crystal structure and doesn't come back to the sensor. And another piece of evidence for that was what I mentioned earlier about us getting a really fuzzy surface that we had to try and extract the final surface from. I think we were getting returns that were basically laser light from the LiDAR sensor penetrating into the snow a little bit, maybe an inch or 2, and then kind of bouncing around and coming back out, which causes you to have essentially what is an inaccurate measurement of the surface. So I think the actual snow crystal, the snowflake characteristics matter a lot.
Wow, yeah, that was an excellent question then. Did you consider using photogrammetry to compare results with the LiDAR for this application? Did you guys play any part in kind of looking at other data sets?
Yeah, we didn't collect photogrammetric data. Like we didn't collect any imagery data, but there was another group of grad students there from Montana State University that were trying to do structure from motion photogrammetry with a camera drone. And so, the data sets that we submitted, the LiDAR data sets that we submitted, I know they are using our LiDAR surfaces to compare the surfaces that they're getting from photogrammetry. That's really tough though. If you're familiar with how photogrammetry works at all, or if you've done any of it with a drone, a uniformly colored surface like snow or sand or anything like that, it's really difficult to get a photogrammetric algorithm to work properly and give you a point cloud that you can extract a surface from. So I haven't heard any of the results of that, what the work that those grad students were doing, but I'm guessing they had a pretty challenging time getting an actual surface out of it. That being said, though, I do just want to remind you, Conrad, we were going to do a sneak peek of our white paper at the end. So let's just make sure. I have a little thing to show once we're done with questions.
Sure thing. Yeah, we've got a couple more questions. Then I'll pass it back to you.
Sure.
We've got a question. How and if patches of ice on top of the snow affect collected data?
Yeah. Well, what were you going to say? Something else there?
I was just going to say it sounds maybe similar to the question you answered a couple questions ago, but go on.
Yeah, it is kind of similar to that. We were talking about the different snow crystal structures kind of influencing the quality of LiDAR returns that you get. I think that carries over to an ice surface too, right? That's just another surface, and that reflects light in some unique way. We did actually do a small sample of, we mapped out the extents of an ice patch that was there on one of our acquisition days and kind of extracted just the LiDAR for that little area to show if the 905 nanometer was working on ice. And it actually was. It was getting us pretty good returns on the top of the ice, which we were pretty impressed with. That wasn't really the focus of the study. We just had the one quick sample that we grabbed because we were like, oh, hey, there's a big ice patch here. You guys might be interested in taking a look at that. So I think kind of more work needs to be done on how LiDAR works on ice surfaces specifically.
Okay, another question here is, how easy is it to classify and remove unwanted points in the point cloud? You said you used TerraScan for that. How easy was that?
Yeah, I guess it was a challenge on this, again, because of all the like grasses and crop stubble that was sticking up, as well as the fact that we had kind of this fuzzy point cloud because of the snow being a challenge for the LiDAR to reflect off of in general. So I wouldn't say it was easy by any means. It was definitely more difficult than extracting just the surface points from a typical topographic LiDAR acquisition that's just on regular ground that has no snow on it. But it can be a challenge. I mean, if you're not too familiar with how LiDAR processing works and point cloud processing, it can be a challenge to get your surface out of even a regular surface that's not covered in snow. Vegetation gets in your way. And so you do have to be familiar with the processing techniques to extract just the ground surface and get rid of things like grasses and shrubs and trees and things like that. But the snow was more challenging than a regular surface.
Okay, thanks. And last question we've got here for today is, was the 1550 nanometer data completely unusable or just way fewer points? And did you try flying 1550 using different parameters to test it out?
That's a good question. We did not fly a bunch of different parameters with 1550, so we didn't do really extensive tests with that. That being said, the sensor that we have that does 1550 can collect way more data than the Minivux system we used, the 905 system. So that the Minivux system, we maxed out the pulse rate at 200,000 pulses per second, but our VUX1 system, which is the 1550 nanometer that we tested, can do about 4 times, a little bit more than 4 times that. it maxes out at 820,000 pulses. So we had it kind of maxed out at that level. And I wouldn't say it was unusable. We got returns on the surface, but it was much, much less dense. You know, there were just way fewer points that were actually on the surface of the snow. And I wouldn't say it's unusable. It kind of depends on how much detail you're trying to capture. You could definitely get a surface out of it, but it wouldn't have been anywhere as accurate or capture anywhere as much detail as the 905 did. And I think for SnowEx and for the specific, you know, mapping goals that we had for this test site using high density drone data, they would consider the 1550 unusable. But if you just wanted kind of a more rough surface of the snow, I think you could do it.
All right. Thanks for answering all the questions, Jeff, and thanks to the attendees for asking those. I'll pass it back to you because you have something else to go over.
Yeah, let me grab this from you really quick. Do I have that back?
Yep, we can see you.
I'm just going to pull up Cloud Compare here. So I don't know if everybody caught it, but in the advertisement for the webinar, we mentioned that DJ&A is currently working on a white paper comparing LiDAR, drone LiDAR, and photogrammetry. So I just wanted to kind of show a quick kind of qualitative example of why we're doing that white paper and an example of why that work matters. As geospatial professionals in the survey industry, you know, we run into a lot of clients and also other companies that do the type of work we do, trying to use cheaper photogrammetry drones to do topographic mapping in comparison to like the LiDAR drone that we use and the types of system that Phoenix makes. And there's some issues doing that in a lot of cases. So this is a project, this is a little clip of points from a project that we did in Colorado. This is Fish Creek Falls in Steamboat Springs, if anybody's familiar with that. And this colorized point cloud I'm showing you right now is a photogrammetrically generated point cloud. So we collected photos with a DJI Phantom 4 RTK, which is a pretty common photogrammetry drone that people use. And you can see how, I'll draw your attention to kind of this draw area where there's a little bit of a stream that comes down in this ravine. There's huge gaps in this point cloud that was generated from photos. And the issue with that, this is the full cloud and you can see all the trees here. But if I switch to just the surface points that we would extract from that point cloud, you can see these gaps even better. And you can see how, you know, clearly if you try and extract a surface from this, you're gonna have some issues where you just simply don't have data because the vegetation's getting in the way, the trees are getting in the way, shrubs are getting in the way, things like that. So just as a quick comparison, I can turn on our LiDAR surface that we collected on the same area using that VUX1 LiDAR system that I mentioned earlier. And you can see how those gaps are immediately taken care of by using LiDAR. And so now you're looking at points that came purely from our LiDAR acquisition. And so it's a much more complete surface, which enables us to have much more accuracy in our data products. So we've been running into this for a number of years now. You know, people trying to use photogrammetry essentially where it shouldn't be used. And there's really not a lot of unbiased resources out there on the accuracy of photogrammetry and the appropriate application of it. So we kind of took the initiative to go ahead and collect those sample data sets. We did 3 test sites where we collected photogrammetry data and LiDAR data on the same exact sites. We have lots of truthing points to verify them all. And the white paper that we have that's going to come out is going to kind of go into these comparisons in depth and present a whole quantitative analysis of that. So if you're interested in something like that, I'd recommend following DJ&A on LinkedIn. That's probably where we're going to post. That's the most likely place you're going to find our post about the white paper when it does come out, probably in January or February or so. So yeah, just kind of wanted to throw that out there, and I thought some people in the audience may be interested in that.
Yeah, looking forward to checking that out.
Cool. Well, are there any other questions we wanted to run by? I think we're pretty much at time here.
I think we're there. Thanks so much again for taking the time to share your work with us. It's been really enlightening. And thanks to all attendees for tuning in. If you have any follow-up questions, you can connect with us on social media or just send us an email. We'll be posting a recording of this webinar to our YouTube channel probably within the next couple days. So yeah, thanks again. Really appreciate it.
Great. Yeah, thanks, Conrad, and thanks for everyone who attended. Happy to share this with everyone.